Hi, third grade. Hope you're doing well today. This is going to be our video for May 11th through the 15th, and it's also going to be our last video for this school year. So when we meet again, you're going to be fourth graders. So that'll be pretty exciting, right? Well, let's go ahead and get our supplies ready. You'll definitely need a pencil. You're going to need your Star Master Quick Review book. You'll also need your fraction packet for your math lab. We're going to be talking about that. And we're going to be working on page 70 today. So turn to page 70 in your Star Master book. We're going to go through these first two questions pretty quickly. Okay. So let's look at number 1. What is the correct name of the figure below? And unless you've studied your three-dimensional shapes, and this is three-dimensional because it has a height, how tall it is, it has a length, and it has a width also on it. So it has 3 ways to measure it. So we have to think about this. This comes to a very pointy top, so we'll investigate that. All right, we want to know the correct name for this figure. It has a base, and a base is what it sits on. So this is our base right here. And I think that's going to help us name this. So our choices are rectangular prism, rectangular pyramid, triangular prism, and a triangular pyramid. Well, I'm pretty sure that when you looked at this, probably the first thing that came to your mind was, that looks like a pyramid. So I'm guessing that you could probably take out rectangular prism and triangular prism. Even though there were triangles in here and there's a rectangle in here, this did come to a pointy top. And when we have a pointy top, it's either going to be like a cone, like we talked about maybe a couple of weeks ago, or a pyramid. The bottom of this tells us what kind of pyramid. Triangular pyramids would have a triangular base. Rectangular pyramids have a rectangle base. And what does that look more like? I think it looks like a four-sided figure, which would be a rectangle. And in my room, if you've ever seen, I have a triangular prism on my wall. So maybe next year you might cruise by and see what a triangular prism looks like. Okay. All right. Let's go to our next problem. It says, a parallelogram always has. So I'm going to underline. I'm thinking through. I don't do anything unless I think through the problem. That's what we call our cube strategy in our class. And so when I look at this, I have to see what my choices are, don't I? So I'm thinking about a parallelogram, and I'm going to have to know what a parallelogram is. We studied right before spring break. We had studied all sorts of words that went with quadrilaterals. So I'm hoping maybe you remembered what a parallelogram was. So A, no parallel sides. B, exactly one pair of parallel sides. C, exactly 2 pairs of parallel sides. Or D, either 1 or 2 pairs of parallel sides. Well, in case you forgot, I wanted to show you a picture of a parallelogram. So let me turn the page here. And this is a parallelogram. A parallelogram, like its name says, must have a parallel top and bottom. That means if I kept drawing these lines, or this line for the top and this line for the bottom, okay, they would never meet. Also, a parallelogram has to have parallel left and right sides. That's the only thing a parallelogram has to have. Top and bottom parallel, left and right parallel, or parallel like this if you want to. So let's go back. How many parallel sides does that mean it has then if we're looking for a parallelogram? It has a pair on the top and bottom, a pair on the left and right. Even if they're leaning a little bit, it doesn't really matter. Okay, so it has exactly 2 pairs. It can't have none. For goodness sake, the word parallel is in the word parallelogram. 1 pair is not enough, and there's never a choice. It can't either be 1 or 2. It has to have exactly 2 pairs. 2 pairs mean when you put 2 things, that's a pair and that's a pair. If you could see me down here in the bottom here. I wanted to show you some more things that can have the name parallelogram though. If you look, a rhombus can be a parallelogram because its top and bottom are parallel, its left and right are parallel. A rectangle can be a parallelogram. Top and bottom are parallel, that's one set. Left and right are parallel, that's another set. And a square can also be in the parallelogram family. The top and bottom are parallel, the left and right are parallel. So not only this picture right here is a parallelogram, but these as well. All right, so let's go to this next page. And this is something that we've seen for the last 2 weeks. Let's make sure we remember how to do it. Randy put new tile on his kitchen floor. A diagram of Randy's kitchen appears below. A diagram is simply a picture. What is the area of the kitchen floor in square feet? Okay, area is always measured in square units. And square units could be like square inches, square feet, square yards, square miles. And we are finding the area. So I want to make sure I remember area. Now, do you remember the formula for area? Area, oh, this is going to be a funky A there. There we go. Area is equal to what? Oh, do you remember? Length times width. Now that you know the formula, I want you to find the area of Randy's kitchen floor. So pause the video, come right back, and see if our answers match. Okay, so pause right now. Okay, did you find your answer? I wanted to show you how I solved. I like to keep the A when I'm solving, and I like to think of the length of something as its long side. So I replace the L with the 11 on the diagram. I like to think of width as the shorter side, and so I replace the W with a 6. And so I have 11 times 6. Pretty sure y'all are pretty good at your times 11s by now. And so our area is 66 square feet because area is always measured in square units, and our units were feet. All right, so last problem on, I think we're on page 71. I didn't say that earlier, but we are on page 71 now. Okay, and here we go. Scott's rectangular bedroom is 12 feet long and 8 feet wide. What is the area of the bedroom in square feet? Once again, you already have the formula for area, and we need to just mark up our cube strategy here. So it tells us he has a rectangular bedroom. That's the only thing that we know how to find the area for, is either a rectangle or a square, as a third grader anyway. When you get older, you'll find areas for other things. And it is 12 feet long, 8 feet wide, so I'm circling the important numbers in my problem. What is the area? I'm going to box what I should be finding here, area of the bedroom in square feet. And if you'll notice, we have one of those type of problems that you have to fill in. I call this a griddable. Find your answer. Okay, so you're going to pause the video, do the work, come right back and see if our answers match. Pause the video now. Okay. Want to show you my work. Maybe my work matches your work. I always like to put my formula down so I never get lost in my problem. So I wrote area equals length times width. And like I told you before, I like to think of the length as the long side width is the short side, and so I replaced the L with a 12 for length, and the width is the 8. I circled those up so I made sure I used the correct numbers. And then I did multiplying. You might not have known how or what 12 times 8 is. If you didn't, I do know that you guys probably been practicing on a 2-digit times 1-digit problem. You may have had to solve that like this. That's fine, but you should have gotten 96 square feet. Now, let's go to our next page. Oops, which will be here. I wanted to do a quick review. This is our final video for this year, so I want to make sure that you have fractions understood before we go to 4th grade. Okay, so I wanted to remind you everything we've learned about fractions. A fraction has a numerator, a fraction bar, and a denominator. The numerator, okay, are the things that you're looking for, the things that you're searching for. We also think of the numerator like the top, like our head. We can nod our head, okay? Nod and numerator start with N. Denominator is the whole thing. It's the big part, okay? So the denominator goes on bottom, okay? And we dance our denominator. And D for denominator also is D for dance. That's the way I remember it anyway. Or north and down if you like that one better. We talked about fractions with whole objects. So we can take whole things like this whole circle, we can cut them up, and we can have a fraction. The way we find our fraction is, well, let me draw a fraction bar out here. We count the total pieces. So 1, 2, 3, 4, 5, 6, 7, 8. I always like to start with the denominator. It's the whole thing. If I wanted the shaded part of this, I would count only the shaded pieces. 1, 2, 3, 4, 5, 6. The shaded part is 6/8. If I wanted the unshaded part, it would be how many eighths? It would be a total of 8 pieces where 2 of them are not shaded. Let's look at this one. How many total pieces? So let's draw my fraction bar. 1, 2, 3, 4, 5. 5 total. That's the denominator. It's the big number in my problem. How many are shaded? 1, 2, 3. 3/5 are shaded. But if my question had asked me about the unshaded part, I would simply say, well, there are still 5 total pieces, but how many are unshaded? 1, 2. 2 are unshaded. 2/5 are not shaded. So that's fractions with whole objects. We also talked about fractions with a set. So I have a set of objects here, a set of Legos. So I have blue Lego, orange Legos. If I wanted to write the fraction for the blue Legos, well, first of all, I always start with my denominator, so I want to know the total amount. So I would say, okay, there are 1, 2, 3, 4, 5. There are 5 total Legos. It's the whole set here. How many of them are blue? That's the part I'm looking at. 1. 1/5 of the Legos are blue. Now I come over here. I'm finding orange fraction, or the fraction of orange Legos. Well, we didn't change the amount of Legos. There are still 5 of them. How many of them are orange? 4 out of 5 are orange, or 4/5. So you can do fractions with a set of things. You can also do fractions on a number line. Now, number lines are a little trickier, but I taught you earlier that when you find fractions on a number line, we count the spaces between the whole numbers. So my number line here just starts with a 0, ended with a 1, and I need to count the spaces between the lines here. So I have 1, 2, 3, 4, 5, 6 spaces. That means that this number line is numbered with sixths, okay? Because there are 6 spaces between 0 and 1. And if I were going to label this number line, I would say this is 1/6 from here to here. If I took another hop, that would be 2/6, and then here would be 3/6, and here 4/6, and here 5/6. And what's cool is I could label this with a fraction too, and this would be 6/6. And if your numerator is the same as your denominator, you have a whole thing. And we do. We ended up on the number 1. So that's how we have fractions on a number line. You count the spaces and then label the lines on your number line. We also talked about equivalent fractions. Equivalent, this big word right here, is just a big fancy word for equal. So equal fractions. This is probably one of the harder things that we've had to learn this year. This right here and this right here, this looks like a whole lot of stuff here. And if I were just to write the fraction for this, well, I know I need the total pieces. So let's count those. 1, 2, 3, 4, 5, 6, 7, 8. Well, there are 8 total pieces. How many of them are shaded? So we're just looking only at the shaded right now. 1, 2, 3, 4, 5, 6. 6/8 are shaded. Well, I come over here, and if I write the fraction for this, I want to count the total pieces first, the whole thing. 1, 2, 3, 4. 4 total pieces. And if I look, how many are shaded? 1, 2, 3. 3 are shaded. Now let me erase my marks in here real quick. And this mark right here. All right. Now, if we wanted to know if these were equivalent fractions, what we would have to do is take a look and see, is the exact shaded space here the same size as this shaded space here? Or is this unshaded space here the exact size of this shaded space? And let me show you. If I took this, oh, those are as one piece. I forgot, I can't move those separately. But if I do this, let me grab a pen here real quick. And if I were to make some lines in here, I'm going to show you something kind of magical here. Whoops, that's not a straight line. Sorry about that. But if you look, don't those look so much alike now? Just by putting a few lines in here, I was able to make it look just like its next door neighbor. And if you look very carefully, okay, let me go back to my lines here. Watch, if I go from here to here, it looks just the same as if I go from here to here. So look, this amount shaded is the exact same size as this amount shaded. Even though they're different fractions, they're equivalent. So 6/8, if you have 6/8 of a pizza, it's the exact same amount as 3/4 of a pizza. And as a third grader, looking at pictures is the way you decide if things are equal. Okay. Now for our final thing, the very back of your fraction book, we have page FF1, and there are 4 FF pages. FF1, FF2, FF3, and FF4. You can add fractions as a third grader, but only if they have the same denominator. When you get older, you'll learn in the 5th grade how to add fractions that have different denominators, but until you get there, as a 3rd grader, all you know how to do is add fractions with the same denominator. So if I look at my fractions here, I have 8/9 plus 8/9. Well, if I come over here, when you add fractions, you never add the denominators. And I'll tell you why in just a minute, but you write the same denominator down. And you take your numerators and you add your numerators up and you get your answer. Now, I know I said that the numerator is supposed to be smaller than the denominator. Well, in this case, it's not. Well, this would be called an improper fraction. But since you added it, it's okay. It's okay to have an improper fraction as a 3rd grader if you're adding fractions. Later on, you'll learn how to turn, later on in 4th grade, you'll learn how to turn improper fractions into something else, something proper, okay? And the reason we don't add the denominators is because if we had the size of 9ths and we had 8 of them, and we had another 8/9, 9ths are the same, okay, 9ths. Well, if you added them up, you would still only have 9ths, okay? You wouldn't have something magical like 18ths, okay? So if I have a set of things that are the size 9ths and another set of things the size 9ths, well, if you add them together, you still just have 9ths. It's like if I took dogs and I added them to dogs, then I have dogs, right? But I couldn't add dogs to cats and get elephants or something. That's how you have to think of the denominator. So if I come here to the next one, 4/5 plus 4/5, well, if I add fifths, I'm just only going to get fifths. And then I have 4 plus 4 is 8. So you're getting the hang of it? Let's go to the next one. If I'm adding ninths, I'm only going to get ninths. And I'm going to see how many I get if I have 2 ninths plus 5 ninths, 7 ninths. This one happened to be a proper fraction, didn't it? It had a smaller numerator than the denominator. Let's go to eighths. If I were to add eighths together, I'm still just going to have eighths, but 1/8 plus 1/8, I'm going to have 2 eighths, aren't I? All right. Well, I think I've shown you enough of those. You have a lot of practice pages. Just remember that when you're adding fractions, your denominator has to stay the same, because these things don't magically change into something else just because you're adding. All right, well, this is our last video. I hope you have a great summer. I hope to see you again when you're in the 4th grade, and it'll be exciting to meet face to face again, won't it? But for now, I'm going to say bye and see you next year, I suppose.